Hi, hello everyone. Welcome back to Deep Learning video lecture series. And in this lecture, we are going to discuss types of gradient descent. Here, the gradient descents are classified into these categories. So in this lecture, we are going to discuss about the major three categories like a batch gradient, stochastic gradient, and mini batch gradient. And one more is a momentum based gradient descent. And we will also, I would also give a brief idea about this adaptive learning methods. There we are going to cover AdaGrad, adaptive gradient algorithm, and root mean square propagation, and adaptive moment estimation. Under the hybrid and advanced gradient descent variants, I will give a brief idea about Adam with a weight decay and Nestrov accelerated adaptive moment estimation, NAG, and AMS grad. So why, on what basis the gradient descents are divided? So we have to just quickly go back, and we have to connect that concept to this today's lecture. That is in the concept of machine learning or a deep learning. What kind of data will be given? That is to train the models. That is the way we teach. So if you look at the data that is supplied to any model that is to train, based on if a data set has output the target variable, then that is we do a supervised learning part. If the data set does not have the target variable, then that is unsupervised learning would happens. So in this case, because our objective of this gradient descent mainly is to optimize the loss function. Okay, how many ways? Because so when we will start with a random point, and then we'll find out the gradient, that is in the slope in which direction we have to move to reach the optimal solution. That is every point we calculate the slope, and then accordingly, and the gradient will be updated. So in order to move to the optimal solution, even for example, that is how fast we are moving, that is based on the gradient. For example, if you take this curve, and the gradient at this point, and the gradient at this point, and the gradient at this point, and the gradient at this point is changing. So accordingly, suppose for example, if you plot this on two-dimensional space where x and y are the variables, if you take and this, that is the rate of change, would be calculated with respect to the x and y. And suppose if you observe this point where this one is, if you take this segment, this part, and if you observe the rate of change in x and rate of corresponding change in y, so this is a rate of change in y, and this is the rate of change in x. Okay, so that's why it looks steep. Even suppose for example, if you take this part also, and in this case the rate of change in x is little bit more than the rate of change in y. Okay, accordingly the gradients will be updated, that is till we reach the optimal solution. So sometimes as we discussed, the gradient it may overshoot, or it may diverge, it may not converge. And sometimes because of the learning rate or the gradient update, and what basis, and based on what information, that means what information that is the gradient would give us to move to the next step, and then next step, and then next step, and what are the problems, right, we will face as we discuss the challenges of vanishing gradient, exploding gradient, and the minima, local minima, and the saddle points. So to overcome all this and to minimize the objective function, and not only minimizing the objective function, and also the other what is the primary objective is minimizing the objective function, and what are the secondary, like suppose if you want to train the model, and then how much time it would take. So how many iterations it required to reach the convergence, like all this matters. So we have to keep all these factors, then accordingly we have to design the gradient descent so that it will be more effective, that is in minimizing the objective function, that is cost function. Okay, so that is the way we use the gradient. But the learning, how we teach the models, that is by supplying either two kinds, as I said, two types of data, like a data set with the target labels, that is for the supervised learning, and without target labels for unsupervised learning. So let us assume that because we are going to calculate the loss, we are going to calculate the loss or the error, that is by comparing with the actual output and the predicted output. So how many times, or what are the samples it is going to consider, that is in this during this learning process. So how many times and on what basis this gradient would be updated, that is the data set size, the number of samples, like whether the gradient would be updated for each sample, or whether the gradient is updated after exploring all the samples, or the gradient is updated for after set of samples. Like based on this, the gradients are divided into the mainly three categories: the batch gradient, stochastic gradient, and a mini batch gradient. So the first one is a batch gradient descent. It sums the error for each point in a training set. That means the point is nothing but a sample. Like suppose a data set has some 10,000 samples, 10,000 rows. So for each row, it calculates the error. Like suppose, let us say there are variables, independent variables x1, x2, x3, and there is an output variable. So this is like there are like 10,000 records of this with these properties, characteristics x1, x2, x3, and the each row, that is a sample, is going to have a output y. So now by using this batch gradient descent, so each point, like suppose let us say 1.5, 2.6 and some 6.7, like this, it's 1 is a output. So we train the model and we'll find out the error, that is when by comparing with the actual output, then the error would be recorded. And similarly for every sample, like 10,000 samples are there in this data set. So for all this 10,000 times, the error would be calculated, and then that error will be summed for each, right? So then updating the model only after all the training examples have been evaluated. After evaluating all these 10,000 training examples, then only we'll update the model. So that is this process is referred to as a training epoch. That means it has to explore all the samples in the given data set. So then the gradient will be updated. So here you can see here, this is like a parameter that is need to be updated, need to be tuned, and this is a gradient, that is with the gradient that is with respect to that parameter, that is a loss function, right? The change of a loss function with respect to the theta. and this is a learning rate. So this is the way we update, but update happens once we complete all the training examples. Means once we evaluate all the training examples, then this model would be updated. So that is a batch gradient descent. So while this batching provides a computation efficiently, it can still have a long processing time because we have to train the data set that still needs to store all of the data into the memory, because we have to process all the samples in the data set. So we need enough memory. So that is a disadvantage with the batch gradient descent. The batch gradient descent also usually produces a stable error gradient and converge. But sometimes that convergence point is not the most ideal, that is finding the local minimum versus global minimum. Next, the type of gradient descent is a stochastic gradient. This stochastic gradient runs a training epoch for each example within the data set, and it updates each training example's parameters one at a time. That means the batch gradient evaluates all the examples in the data set and then it updates the model, whereas stochastic gradient, for every example, like for every sample in the data set, it updates the model. So that's why we may not find a smooth curve when we connect all the gradients. So that is the one observation you can easily understand. So like here you can see for all the samples where xi, where I is in between, like suppose there are some 10,000 samples in this data set, then I is in between the 1 and 10,000 samples. So these many times the parameters would be updated, the model would be updated. Since we need to hold one training example, then we can easily store that simple sample in a memory. But these frequent updates can offer more detail and speed. So it can result in a losses in computational efficiency when compared to batch gradient descent. So its frequent updates can result in noisy gradients, but this can also be helpful in escaping the local minima and finding the global minima. So next category is a mini batch gradient descent. So mini batch gradient descent combines both the concepts from both the stochastic gradient and a batch gradient descent. Here for each batch, like suppose the batch size is let us say some 100 samples. So after evaluating the 100 samples, then it will update the parameter, it update the model. So when we compare this with that means the stochastic gradient is again we would consider it as a mini batch gradient where the batch size is equal to 1. Whereas the batch gradient also would be considered as mini batch gradient where the batch size is equal to the number of samples in the data set. So this mini batch split the training data set into the small batch sizes and perform updates on each of those batches. So this approach strikes a balance between the computational efficiency of both the batch gradient descent and the speed of a stochastic gradient descent. Next, momentum based gradient descent. So it uses an exponentially weighted moving average of past gradients to smooth updates. Like so far we discussed the the gradients like a batch gradient, mini batch gradient, and stochastic gradients, they update, that is the model or the parameter would be updated based on the current value and based on the gradient. Okay, every time we subtract the gradient from the current value, like suppose weight would be updated based on its current weight, that is old weight, right? And then we that is old weight minus a learning rate times the gradient value. But here in this case, the momentum based gradient descent, like suppose that means, like suppose let us take this diagram. When we drop a ball here, it is continuously falling down while moving, right? It gets the momentum, and so then it may go up to this point and again oscillates and then settle stable at the center point. Let us say this is a local global minimum. Okay, so in order to avoid these problems, so we have to take the information from the previous, that is a past gradients, and accordingly we'll update this so that we'll avoid this kind of problem. So here we can see the velocity would be calculated, and then based on that velocity, that particular parameter would be updated. So the momentum term increases for dimensions whose gradients point in the same direction, and reduces updates for the dimensions whose gradient change directions. So that is the momentum. We have to control the momentum. How this momentum based gradient controls it? That means it increases for the dimensions whose gradient point in the same direction, and reduces updates for the dimensions whose gradient change directions. So as a result, we gain the faster convergence and we could reduce the oscillations. Next is the Nestow accelerated gradient, in short NAG. It improves the momentum by computing the gradient ahead of time. Like the previous momentum based gradient descent, based on the previous gradient, it would update. Whereas in this Nestow accelerated gradient, that is, this simply improves the momentum by computing the gradient ahead of time. So here you can see, like if you break down this entire equation, that's this equation, then so let us it first find out the look ahead gradient, the point, that is this is a momentum factor, this is a velocity, so it finds out the look at like suppose, and this is, we are talking about the weight or the parameter weight. So it find out the look ahead and then calculate the gradient with respect to this look ahead point, and then it find out calculate the velocity would be updated like this, and then it update the weight, that is W, that is equal to W minus Vt. Next, adaptive gradient algorithm, ADAGRAD. It adapts the learning rates based on the past gradients. Next type is root mean square propagation, this is RMS prop. It improves the ADAGRAD by using a exponentially decaying average of the past squared gradients. These are all like in detail because we need to spend again some lot of time on each type we have to discuss more mathematical part, and also some the limitations, advantages, all would be discussed in the coming lectures. Next, adaptive moment estimation is which combines the momentum and the RMS prop. So these are all the equations. You can see like there is nothing new in this case, but the overall how the gradient is calculated, and to avoid the challenges in this. Next, Adam weight, that is weight decay Adam. It improves the Adam by adding the decoupled weight decay, that is to prevent the overfitting problem. I think we discussed about this overfitting problem in another course, so data mining. So it mainly separates the weight decay process from the gradient update. Next, AMS grad. This is again the stochastic optimization method that seeks to fix the convergence issue with the Adam based optimizers. So AMS grad uses the maximum of a fast squared gradients, that is VT, rather than the exponential average to update the parameters. So the corresponding equations you can see. So we'll discuss like in the coming lectures about what are all these, and because I will show some demos also, like how by changing the all these parameters, how the model learns, how the learning rate affects, how all these parameters like the momentum factors affect, and how the velocity would be, and if we change the learning rate. And one more thing, like in this types of gradients, like few gradient descents we use the constant learning rate, but sometimes it may not be the right option. So in that case we have to use the different learning rates. That also we will discuss in detail. So thank you for watching this video.